Hey guys, welcome back to another chemistry lesson here as we wrap up our equilibrium unit. Today we're going to look at something called the common ion effect, which is exactly what it sounds like. It's if you have an ion in common in a solution. So far we've looked at the solubility of substances in pure water only. So if I wanted to take salt, put it in pure water, look at its like KSP value or its molar solubility, go back and forth, be able to figure the other one out. Now, the common ion effect is when you try to dissolve a substance, but one of its ions are already present. So I'm not using pure water anymore. I've already got something in the water, and now I'm going to try and dissolve something in there. This is really common if I had a beaker, for example, I was doing some chemistry. I'm going to want to dissolve two things together to have them react, right? I don't just put salt and water. I'm like, hey, look, I'm doing science. Well, I'll put salt and water and something else and see if they react. But if there's some common ions, if there's some crossover there, let's like say I was using silver chloride and sodium chloride. Whichever one I put in first, I've already added chlorine ions to that liquid. So when I go to dissolve the other one, that chlorine ion is already present. So what that's going to do is reduce the solubility of whatever that second thing that I'm adding is. Well, technically it would reduce the solubility of both. So our example, dissolving silver chloride in salt water. So here's silver chloride. Should be giving us silver ions plus chloride ions, right? Both aqueous. But if it's salt water, that means chloride is already there. I've already got a bunch of chlorine from the salt I've added, sodium chloride. So what I'm effectively doing when I add the sodium chloride is I am increasing the concentration of chlorine concentration. So if you guys remember back to Le Chatelier's principle, if I increase the concentration of one of the reactants, what happens? Well, Le Chatelier says if you add a stress to a system, you've got to try and get rid of that stress. And so to get rid of that chloride, the whole reaction is going to shift back to the left. I should have had a double-headed arrow there because this is an equilibrium one. And so I'm going to reduce my chlorine a little bit, reduce my silver a little bit, and increase the amount of solid I have. So Le Chatelier's principle says if I try to dissolve silver chloride in something that already has chlorine or already has silver ions in it, it won't dissolve as much. The reaction is going to shift back towards the reactants, which means I have more solid, which means I'm not as soluble. I will have less dissolving because of the common ion that's present. And this kind of makes sense if you think about it. If I had a glass of saturated salt water, so it's got full as much chlorine as it can fit, and I try to add more salt. Let's just say my second quote unquote reactant is salt again. None of it's going to dissolve because it's already got all the sodium and chloride it could take. Those common ions mean you're not getting any extra stuff dissolved. And so it kind of makes sense. It works both ways so if you were to add salt to an already saturated solution or if I were to add silver chloride. Now, some of the silver chloride would dissolve because I don't have any silver in there yet. I would just be looking at chlorine. But you kind of get the idea. Less of it would dissolve as it would normally in pure water. So what does that look like if we actually have to do a calculation? So here's silver chloride. We give you the KSP. 1.6 times 10 to the negative 3. That's my KSP? Doesn't seem right. Let me double check here. I thought my KSP was smaller than that. KSP. 10 to the negative 10. There we go. I knew there was a typo there. Can I change that? Oh, well. I'll just crush that. It should be 10 to the negative 10. That's my KSP. I want a very small KSP to make a point here. So, first of all, before you even look at your ice chart, KSP 10 to the negative 10, you know that it's already not very soluble. We want to stay kind of towards the silver chloride side of things. So what is its molar solubility going to be if you dissolve it in 1.5 times 10 to the negative 3 molar solution of silver nitrate? So this is what I want to do. But I've got silver nitrate. I already have silver ions in the solution. So we're going to solve this with an ice chart. We can ignore this, because it's a solid, so I only have to look at the silver plus and the chloride minus side, because they're the only ones that are aqueous. But the only difference here is I'm not starting at 0 for all my reactants, right? I've already got this much silver from the silver nitrate. If you take a look at silver nitrate, it's just AgNO3. So you should double check this, because if this was like Ag2NO3 or something, then that you might have to look at the mole ratio to change how much of that's actually in it. But it's a straight up 1-to-1, which is really nice, makes things easy. So I actually am starting with 1.5 times 10 to the negative 3 as my concentration of silver, and there was no chlorine in there. Silver nitrate doesn't have any chloride, so I won't have any chlorine ions floating around. I double check my equation up here, and it's a 1-to-1 ratio for everything. So I'm going to be making some silver, and I'll be making some chlorine. So at equilibrium, I'll have 1.5 times negative 10 to the 3 plus x, and my chlorine will just be positive x. All right, fantastic. Let's plug that into our KSP and solve, right? Hold on, before I go to that step. If you're to plug this into your KSP and solve, here's what you're going to get. KSP equals 1.5 times 10 to the negative 3 plus x times x. Now, x times x is x squared. I have an x squared term. I have no way to get rid of it. I have to do a quadratic equation to solve this. And we don't like quadratic equations, generally speaking, because they're a bit of a pain. There's a lot of math going on there. There's a lot of places you can make an error. So there is a trick that I'm going to show you guys to get rid of the quadratic. Now, this isn't a math trick. It's not like square rooting things to get rid of it, just rearranging the formula to make the quadratic magically disappear. It's actually like kind of a logic trick, if that makes sense. And it's one of those things where if you put it in context, if you realize what you're actually doing, you can apply logic to get rid of something. So here's what I mean. Math trick, logic trick to avoid quadratics. Look at this equation. 2 plus x times 2. Now, if we knew that x was going to be really small, let's just say 0.0001, do we need to even bother with it? If you ignore it, if you say x, you know what, it's too small, I'm going to ignore it. My equation is just 2 times 2. My answer is 4. That makes things easy. I like that one. If you include the x, the answer is 4.0002. Now, given whatever the context of this question is, if you're rounding to 1 decimal spot, 2 decimal spot, even 3 decimal spots, guess what? That 2 doesn't matter at all. The answer's the same. If you'd ignored x, all it would have done is made your math easier and not changed your answer. So ignoring x in this case would be a good thing because it makes your math way easier and doesn't actually change your answer out to like the 4th decimal place. It barely changes it. We can apply that same logic of like, if x is not going to make much of a difference here, if this x is really small, we should be able to just ignore it and it won't change our answer. So here's our equation, right? So if whatever I'm adding x to, if x is way smaller than this number, I don't need to bother with it. So if x is really small, we can ignore the x that is being added. I mean, you could ignore it if it was being subtracted or 2. Any adds or subtracts, if the x is small enough, you can get rid of it. You can't ignore the one that is multiplying, however, because 2 plus a very small number is basically still 2. 2 times a very small number is definitely not 2 anymore. Multiplication makes a big difference, no matter how small x is going to be. Actually, the smaller x is, the bigger the difference it makes. So you can't ignore this x. The multiplied x has to stay. But in an ideal situation, if things are right, if things are good, we can ignore this particular x. So that leads to the question, how do we know if things are good? What does that mean? How do we know when we are allowed to ignore x? Now, there's a whole bunch of different rules here. The rule that I'm going to give you guys, the general rule that I'm going to use for this, is if the number you're adding to x, so whatever this is, that's the number I'm adding to x. Oh yeah, I wrote it in there. If it is at least 1,000 times bigger than the value of x. So if that's 1,000 times bigger than x, x is not going to make a difference out to at least 3 decimal points. So let's not bother with it. Now, if you go to take more chemistry, don't be surprised if you see this rule applied in different ways. Everyone uses a different rule for when you can ignore x. Some people say if the x is 5% of whatever you're adding it to. Others want it 500 times smaller. Now, those are both great. They'll work just fine. But the 1,000 times rule is much simpler mathematically because it's just 10 to the power 3, which means all you have to do is look at your exponents and you can tell right away if it's 1,000 times smaller or not. So to find out if x is going to be, well, I guess, yeah, how do we know what x is, right? X is unknown. We don't know what it means. So if you want to find out if x is going to be small enough to ignore, you look at KSP. Because remember, KSP tells you what the solubility is, what the change is. So if KSP is really, really, really small, that means x is going to be really, really, really small, right? If KSP is way less than 1, very little is going to dissolve, which means your change, your x, will be very, very, very small. If KSP is really big, you'd expect a lot of stuff to dissolve, which means your change is going to be really big. So here's our rule of thumb. If KSP is 1,000 times, or 10 to the negative 3, in this case 0.0001 times, 0.001 times, if KSP is 10 to the negative 3 less than the number you're adding x to, you can ignore it. So in our example, KSP, let me rewrite that. Oh, that's ugly. 1.6 times 10 to the negative 10. That's our KSP. So we're thinking, okay, that's a pretty small KSP, right? 10 to the negative 10. We're probably not going to get very much change there. What am I adding x to? 0.0015. I'm going to write that in scientific notation because it makes it easier to read. So you need to check, is this number 1,000 times smaller than this number? And you don't have to do any fancy math. All you have to do is check the exponents from negative 3 to negative 10. So we're checking if 1.5 times 10 to the negative 3 is 1,000 times bigger than this, which basically means if this exponent is at the negative 7 or negative 6, negative 5, negative 4, negative any, if it's 3 greater, you're good to go. So just look at the exponent, right? 1,000 is just 10 to the power 3. If the exponent of KSP, that's up here, is at least 3 less than the exponent here. So is negative 10 3 or more less than 10 to the negative 3? Well, yeah, it's way less. It's 7 less than 10 to the negative 3. Then you can ignore x. Which leaves us with this. Let's just rewrite this whole thing. So KSP equals 1.5 times 10 to the negative 3. Usually it was 10 to the negative 3 plus x, but we're ignoring that x because it is so small, it will not make a difference to our final answer. So I plug in my value for KSP, 1.6 times 10 to the negative 10 equals 1.5 times 10 to the negative 3. I mean, that's just x. I would divide both sides by the 1.5 times 10 to the negative 3. So I'll grab my calculator here. 1.6 times 10 to the power negative 10 divided by, in brackets, 1.5 times 10 to the power negative 3. Do not forget the brackets there in your calculator or it will screw you up. So I divide both sides by this, divide by this, and I get x equals 1.07 times 10 to the negative 7. That sounds about right. And so I want to know, what was the question again? I forgot the question. Always go back and reread the question. What is its molar solubility? So what is the actual molar solubility of silver chloride going to be? Well, we just found out what the change is going to be, so we know how much chloride is going to dissolve. We use the KSPs. Yeah, so I think we're good because it's all 1-to-1 ratio stuff, right? And so that's kind of the trick. It's kind of about I mean, you can do it with a quadratic if you want. if you solve this out as x squared plus 1.5 times negative 3x plus 0, technically, equals KSP, and then you move the KSP over and you set it up, you do the quadratic, you should get the exact same answer for x. It would be off by like 0.000000001. By the time you round, that'll disappear. You won't even see it. And that's because of the fact that this x is so small compared to that number that you can just ignore it there. You don't have to worry about doing it like that. And so that wraps up our... I feel like I'm missing a step here for some reason. No, I'm pretty sure we're good. I'll think about it. So that wraps up our molar solubility, our common ion effect stuff. So keep that little trick in mind if you don't want to do some quadratics. It'll save you some math time. And I will talk to you guys in a little bit.